Okay folks, we're back. You can tell from my attire that either I've been wearing the same clothes for many days, or I'm simply making this video on the same day that I made the introductory one, which is the case. So let's try to see if we can finish kinetics. And actually this video should be pretty short because we don't have that much to do, so it's kind of nice. So to get organized here, so some things you're going to want, the slides that we have, there's really not much left on the slides. In fact, the last slide from the PowerPoint slides has only, I think, 3, 4, and 5, activation energy, reaction mechanisms, and catalysis. You can write those headings down if you want to, but you don't really need to do that. But it's the last slide if you download them. I'm not going to number them here because I think it'll just make things a little less confusing. I'm also going to actually do one of your homework problems here with you, or for you, however you want to look at it. So problem set number 4 from the Kinetics chapter, from chapter 12, so you'll want access to that. You already have access to the introductory video, so make sure you have that ready to go. And this checklist is on D2L, but if you want to stop the video, you can do that and write this down on your own if you want to do that. So these are the tasks for the week. And I don't think it's actually, I'm going to see if we can finish this in a few days because I don't think it's going to take that long, so we're almost done. So if you want to read sections 12.5 to 12.7 in your book, and they have lots of problems that are already worked there for you. So for example, if there's a graphing activity where you get a slope, which I'm going to show you how to do, redo the activity and just see on Excel or whatever you have access to, a Google Sheet, or even your calculator in some cases, and just rework the problem and get the answer that you get, because I'll expect you to be able to do those problems. Watch this video, it's going to be short. You have a set of data that I mentioned in the organization video. I reposted this on D2L under the Getting Started Online tab, you'll see it. You just want access to that. The last worksheet there is what we're just going to briefly refer to. It's making a graph. And I'm not going to make the graph here. I'm just going to show qualitatively how to get the slope of the graph, which you should already be able to do. And we'll go from there, but I'll get to that. So other things you're going to want to do this week is to submit problem set number 4 to the assignments Dropbox. So I'll put a Dropbox there, and then we're going to look to take a test, quiz, probably somewhere in the middle, so it's cheap to call it a quest, somewhere early in the week, maybe Wednesday evening. But let's just get started and see how things go. Also, one thing you can tell me about in the Students Lounge or email me, I think this whiteboard is actually big enough that I could project my PowerPoint slide here and then do additional notes here, if that would be helpful. I don't want to do a 50-minute lecture because I think that would get old after a while, but maybe I could do mini lectures where we do a mini lecture, we do some problems, and then I have you go do homework problems. So we chop it up into mini lectures and then go do homework problems to reinforce it. Maybe that would work. So if you have an opinion about that, you can post something on the Students Lounge or let me know. So I'm going to try different things. But for today, this is pretty easy. So here's problem set number 4, homework problem number 1. We're just going to do this problem partially as a review, partially as a transition from qualitative aspects of activation energy to quantitative aspects. So I'm going to kind of whip through this one pretty fast. So this is homework number 4, and of course you're going to want to write this out. Please don't just skip this problem. So we did this early on, and I used a specific example of a 3-step mechanism for hydrogen peroxide decomposition. So if you want to stop the video and go look at your notes on hydrogen peroxide decomposition, that's a very specific 3-step mechanism, so 3 steps that you add together, kind of like half reactions and redox to get an overall one. This is a generic activation energy profile of chemical A turning into chemical D in 3 steps. Okay, well, so that's what's happening here. So we put potential energy on this side. This is sometimes called the reaction coordinate, and I think in this particular example it calls it reaction progress. It's the same thing. So chemical A starts out with a certain level of potential energy, and in this case, chemical D ends up at a lower energy. So the final energy minus the initial energy is going to be negative. This is going to be an exothermic reaction. If D was above A, that would be an endothermic reaction. So that's the final state minus the initial state, kind of like a delta H or even a delta T. Okay. So then what we have happen here is this goes through one transition state and forms the first intermediate, a second transition state and forms a second intermediate, and then goes through a third transition state and, oops, I made that wrong. That's actually an important mistake I made there. So this is called a transition state. You remember that symbol. So, and it turns into intermediate B. We have a transition state here, and we could label this transition state 1, transition state 2, transition state 3. So it goes intermediate B, intermediate C. Okay. So this is a 1, 2, 3 step mechanism. It's generic, it's just A's, B's, C's, and D's, but it makes the point. You can answer some of those questions there. We already did some of that, okay? The activation energy for each of these is how high, basically, this hump is. Okay, so activation energy 1, activation energy 2 for the second step, activation energy 3 for the third step. This is kind of stuff we've already done, so this is a bit of a review. Okay? The second step has the highest activation energy. Which implies the second step, the second elementary step, to be more precise, the second elementary step in the reaction mechanism. Got to piece all these words together. Writing a short essay might not be a bad way to do this problem, A through B, like write a paragraph, not just answer, 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 answer. In fact, that's a better way to do this problem. So the second step is what we call the rate determining step. It's the slowest step. A reaction is only as fast as its slowest step. So the second step is the slowest. It's called the rate determining step. Okay, so I think that is somewhat of a review. We also have, we talked about this, a catalyst. A catalyst speeds up a chemical reaction. Okay? But it's not a reactant or a product. What does that do? Well, a catalyst, and this is going to be really messy, actually catalysts lower, the activation energy. So they bring that thermodynamic barrier down. And it may not do it for all 3 steps. I just put it there for emphasis. So if you wanted to do a reaction profile without catalysis and then with catalysis, catalysis lowers the activation energy. There's lots of different ways it can do that on a molecular level. We're not getting into that too much detail here, but just know that catalysts lower the activation energy. And that's how you would draw them here. Look in your book. Those 3 sections there are fantastic for explaining it a little bit more organized than I do, but that's nothing new. You're used to that. Okay, so the next thing we're going to do is how do you determine an actual number for activation energy? Fortunately, it's a skill set you already have, so we're going to make this quick. So what you want to do is get the, where did I put it? Oh yeah, you want the data from I'm just going to outline this because you know how to do it. And I'm going to erase this because I don't think we need it anymore. So that's qualitative activation energy. So that's all the qualitative stuff. I wanted to leave that there, but it's going to get too messy. So quantitative activation energy. So I'm going to go to my notes. Okay. If you're following the slides that I've given you, this is number 3. On the slides, you don't have to do that. There's an equation called, and it's in the book, it's a really good part of the book. Okay, this is called the Irradiance Equation, named after a Swedish chemist Svante Arrhenius, who also was one of the early people that recognized man-made or anthropocentric, better word, contributions to climate change with carbon dioxide back in the early, I think it was the mid-1850s. He recognized that this was going to be a problem down the road. So what this is an equation that relates rate constant we've already messed with those with integrated rate laws, methods of it. So rate constant to temperature. Now this is not an equation I'm going to ask you to derive, I'll give it to you. So here's the equation. It's an exponential function. We've seen exponential functions already. Everything in this equation you've already seen, at least symbolically. K is the rate constant. A, I'll talk about in a minute. EA is activation energy, and we'll get the units later. R is the ideal gas constant, but we're going to use, T is temperature. They always put temperature in Kelvin. That's a given by now. Okay. And R, we're going to use the different version of this, is 8.314 joules over Kelvin mole. Okay, this constant in front is called the frequency factor. What does that mean? That's sort of a catch-all constant that takes into account how many times the molecules collide with one another over time. It's not something I'm going to really talk too much about. The position in which they collide, so how many times they collide, are they hitting in the right orientation to react? All of those things are sort of lumped together into that factor. But that's something we're actually not going to have to pay too much attention about. What we're actually after with this, how do we calculate activation energy? That's what we want. Okay, well, you could solve this equation, sure. There's a couple different ways to do this. What I want to show you is kind of like what we did before. I'm going to take this equation and turn it into something we know something about. Y equals mx plus b. We make a graph, we get a slope, and we get an answer. We've done this before with integrated rate laws, but now we're going to do this with this activation energy. How we're going to do that is very similar to something we did several weeks ago, where we took the natural log of each side. So I'm just going to kind of quickly go through this. So I'm going to take the natural log here and the natural log here, and we're going to get natural log of k. This is actually pretty easy. Equals, I'm going to rearrange this. Now, when we take the natural log of two things that are multiplied, it'll be the natural log of A plus the natural log of this whole piece. But natural log and exponential are opposite functions. So what we end up getting is this, negative EA over R. Okay. I'm just rewriting this in a slightly different fashion. Over 1 over temperature. Actually, that's a pretty easy derivation. We're just taking the natural log of both sides and rearranging the terms algebraically, because activation energy and R are constants. So we bring those out in front, kind of like a coefficient, like 3x. So we just pull that out in front. The variable is 1 over temperature. That's the thing that varies. So we leave that as, okay, well, check it out. That's your Y, that's your M, that's your X, and that's your V. So we've used the natural log to take this formula and convert it into something we can make a graph from. So actually, here's where I'm just going to kind of give you the answer. So go find this data. Go find that data on that spreadsheet. And what we're going to end up doing is, I'm pretty sure on that spreadsheet, you're given a bunch of K values and you're given a bunch of temperatures. And I think the temperatures are in Celsius, I don't remember. So convert each of those to Kelvin. Okay, I think you know how to do all this. Take all the rate constants and take the natural log. Remember that formula? Equal sign, ln, then you put whatever cell it's in, A3, and then fill down and get all those. Take all of your temperatures, and let's see, you're going to do 1 divided by whatever the cell is, plus 273.15. So you make sure you put in that formula and convert all the Celsius temperatures into reciprocal Kelvin temperatures. Take all the Ks and convert them into natural logs of K. Then make the graph. This has no units. And this will have units of inverse Kelvin. And it should be a line whose slope is negative. So if you do the graph properly on Excel, we should give this a title, I suppose. I'll leave you for that. So then you can get the slope of the line. Remember how to do that. Equal sign, slope. You choose your, oops, it's not slop, slope. You put your X data in, put your Y data in, and it'll give you a slope. It should be negative. Okay, now so you can stop the video and make this graph and get a slope. Okay, we're back. Let's say you magically have done that, and the slope, I think I have it here. Yeah, you should get negative 2.23 times 10 to the, it's a big number. It's a big number. 10 to the 4th. Well, it's a big number because these are really small, and it's y over x. Okay, so it's going to be a really big number. So negative 2.23 times 10 to the 4th. So just make sure you get that number. And the units on this are going to be y over x. X is already, so the units there are going to be Kelvin. Okay, well, so what? What does that mean? Well, what that means is that the slope, negative 2.23 times 10 to the 4th Kelvin equals that. Because that's the slope right there. So we just take this piece and equate it right here. Negative EA, that's what we're solving for, by the way, divided by R, which has a value, 8.314 joules over Kelvin times moles. And you can do that math. That math is easy. Okay? Negative times a negative is a positive. Just multiply. Okay, that's easy. You've done that math. And what you come up with here is therefore activation energy, and the units are going to be joules per mole, which makes sense. It's an energy. How many joules per mole does it take to conduct the reaction? And I came up with 1.85 times 10 to the 5th joules per mole. Check that, please. Always check that, even on the video, which I believe turns out to be, because we use kilojoules a lot, 185 kilojoules per mole. So what that means is that this chemical reaction that we're doing, I'm not even sure what it is. I think it's peroxide decomposition. It doesn't really matter. The thermodynamic barrier to get over to make this reaction work will be 185 kilojoules per mole. So that's something I expect you to be able to do, is to graph the data, get a slope, and just do the calculation. There's a couple of variations in the homework where you're using this calculation. And the last thing I'll show you is, this is kind of hard to do on a test, kind of integrated rate law and the Clausius-Clapeyron equation from a while back. Don't worry about that if you don't remember. There's actually a 2-point version of this, which I guess I can write it down here. And I'm not even going to go through that because I think you've seen it before. So that'd be the long way. There is a 2-point version where you only need 2 Ks and 2 temperatures rather than a whole graph, so you just have 2 of them. And I'm just going to give this to you. It's the natural log of one of the rate constants divided by another rate constant at a separate temperature equals EA over R times 1 over T2 minus 1 over T1. And again, these are Kelvin temperatures, so you can be given 2 of these and 2 of these and solve for activation energy. It's a little bit easier than making the graph, or maybe not actually, but that'd be the 2-point version and then the graphical version. And that's it, folks. That's it for chemical kinetics. So, be able to apply this equation. This one maybe, I think there's one homework problem that asks you to calculate the factor. Okay, that's fine. Make a graph, get a slope, do that. That's fine. And if you really want to, the exam 2 checklist that you already have, I think I posted it a while back. I know we have a lot of stuff moving around here. Has all the expectations for what you should know on kinetics. So again, make sure you read that, watch the video. Well, we already did this, just make sure, well I guess we did that already. Just make sure you can do it. Finish those problems off, and there's another one in there, I think. Yeah, there's another one of these, number 4. In problem set 4 is one of these 2. And I think you're given the, I'm not sure if I give you the answer or not, but okay. So there's some more of these you can work on. I think that's it. And then let's see about how we're going to take a quiz, and then what we're going to do for a test on solutions, molarity, molality, mole fraction, all that stuff, colligative properties, boiling point, elevation, freezing, all that stuff. And then kinetics. That was supposed to be exam 2. Let's figure that out later, okay? I have a feeling it'll probably be a take-home exam. We'll just keep it simple. Probably won't be worth as many points as a regular exam because it's hard to do that. And we'll come up with some way for thinking about that. But first things first. Finish kinetics. Let's get a good start. Let's get into a routine. Let me know if you have any suggestions. Once this is done, we'll start with chemical equilibrium, and we'll probably end up cutting down on the content because we have 2 major topics left to do in the semester, and we'll end up probably reducing it a little bit. So, take care, folks. Stay healthy, stay well, and I hope to see you face to face. This is fine. It's not nearly as interesting as seeing you in class, okay? Take care. Bye-bye.